Well, the title says a novel approach to nanoindentation using Multiprobe system. Well, it's novel in the sense that we're trying two probes and trying to measure two different things, one being force, one being the distance. I put those two pictures up there to show why we're doing this before I even get into details. This is, what you see there is actually a bunch of cancer cells on top of PDMS pillars, which are 5 micron diameter and about 20 micron tall, so about the aspect ratio of 4. And the reason the cancer cells are up there is to, when they actually are in invasive mode, it is known that their attraction forces are much higher than normal cells. So our idea is to be able to measure by looking at the dynamic change or how much they pull those pillars, try to measure the forces that those cells actually create on the surface. Thus, how invasive they are. So that was the starting point for us to actually go into PDMS and go into how we can actually quantify that force. On the left is what the multiprobe system we have. We have Multiview 4000. On the left, there is a tuning fork with a diamond indenter attached. And on the left, another probe which has a regular AFM probe. The probe is touching to the top of the diamond. And what we do is we move this diamond down and indent. And then while this is fixed, and then we move the stage up and then try to measure any change of the diamonds so that we can actually have the X change or Z change in that case, but in the force calculation X change. So for that, we try to, we say, okay, I need to know the Young's modulus of the PDMS so that I can calculate I can look at the deflection of the PDMS pillar and I can calculate the force. But the Young's modulus of a PDMS, which is in pillar format, with a high aspect ratio, may, or in fact what we believe is, will be different than the bulk parameter Young's modulus. So that's why we want to measure that through nanoindentation. And regular nanoindentation tools, as Aaron was saying, AFM tools, Afm Cantilevers are used. There are so many problems with them, so we had this tool in-house at RIT, and we wanted to make use of it so that we can actually do a better characterization. So, and then after that, so Kit actually touched upon how AFM tips are not good for nanoindentation. And obviously, there are models. This is Oliver Parr that he showed. What you do is you indent on a material, you pull it back slowly, and you look at how much you can get in, which is the H max. And then at that point, you measure the maximum force you measure, and then you slowly pull it back. And then now you see that you have the slope. Slope gives you the stiffness. And then at the end, if you have the plastic deformation, then you have HF, which will, through the force calculation, and then through that, it will affect your Young's modulus. So that was the main idea that we were doing. And then in Kit's case, he used PDMS as a standard component to measure the Young's modulus with different methods. In our case, PDMS is our only method, but we don't want to tune our system on PDMS only. We want to have other materials which are known, which have known Young's moduli, and force calculations that we get from the machine is more reasonable or more correct or dependable. Then we can actually apply that system on the PDMS. Thus, we actually did silicon and then diamond probe indenting on top of silicon and creating some indentation and calculating that. So that's hard materials. Generally, Oliver Parr you can use for hard soft, but mostly if you have a plastic deformation, it's actually good. And if you have no plastic deformation, you're in the elastic regime. There are known methods that, as again Kate mentioned in the morning. why nanoindentation is being done these days? Mostly cytoindentation, a lot of tissue, a lot of, and someone in the morning mentioned, oh actually Kit mentioned that mice is focus, right?
The aorta, yeah.
Aorta, yeah. Sorry, aorta. So most of the biological materials, we don't know how stiff they are, we don't know the properties of them. But if we can measure their properties while they are healthy, and then we can measure when they are not healthy, this could become a detection instead of just measuring the stiffness of the blood cell or stiffness of the aorta. And also, thin film, ultra thin films are used a lot for nanoindentation is used for mechanical characteristics. Our earlier works in 2003, 2004 were on bilayer cantilevers, where we had very thin layer of silicon dioxide and also on a very thin layer of aluminum on it, so we can create cantilevers where you can excite, you can change the curling. Dislocations are very key in ultra-thin films. Because of dislocations, their Young's modules are different, so you cannot just take the bulk modules. That's why we actually work on the characterization of those thin films. And briefly, as Aaron and Keith mentioned, there are Afm cantilevers which are used for nanoindentation. And the main problem is snap-on and pull-off instabilities, where you touch and you release and you shake. Obviously, you have oscillation. Bending errors, definitely, if the Afm cantilever will bend. And another problem where is you're pushing down, even it's not just going down in this direction, it also moves in the other direction, which you don't necessarily count. So those are the things that are generally problematic in those probes. There are non-Afm methods as well, where you have mechanisms to apply force and also measure the force. But then the problem with these is the contact point, z equal to 0 point, it's not clear. If it's not clear, then your experiments are not repeatable again. So, as I said, we want to make sure that our system is producing good force calculations through the indentation probe, and also getting good distance measurements from the Afm probe. So for that, Aaron and Andre and Hisham, we all got together. We actually had the system in that basically put on a sample. We put the probe here to see the stage is moving right or not, and then we put the Afm probe on top, and we did indentation on a silicon. We actually got good results initially on this system, where if you, it's hard to see, but this is the diamond probe, and that's the Afm probe on top of the diamond probe. And we used silicon, which has the 100 orientation, and then we had the diamond probe is 90-degree cube corner diamond indenter. Now, here's what we got from our initial measurements. So this red line is actually, it says 0 to 200, but I put these just to make sure. What happens is you go down first, 200 nanometer, and then go up until you touch the diamond, and then push the diamond up about 200 nanometer. Now, this is the stage value of, so 0 to 400 nanometer. In actual physical world, this is minus 200 nanometer to 200 nanometer. The blue line, on the other hand, which is the tip on top of the diamond, measuring the displacement. See, it's 0 here because the stage didn't touch the diamond yet. And as soon as it touches the diamond, it starts moving up. 200, around 200, and then going down. Now, if there is a plastic deformation, that may not be 200, it would be less. And then once we go down and still measure, and here you can actually read some value for HF before even scanning your indentation. And as Kit was saying, the way the Nanonics tool actually calculates the force is through this formulation. And it does not, it's not like F equal to Kx, right? It's different. So it's good and bad at the same time, because since they are all mingled together, you don't have a separation. So in a way, we are sort of trying to create that separation. While doing the indentation on a known sample, if I can make sure that this force reading is accurate enough, and then while measuring the actual displacement, I may actually use the Oliver Farr model a lot better, other models a lot better, using the force value and the displacement, rather than just depending on whatever I read. And this is our load-unload curve for the silicon. And if you look at the values, there are 100 micronewton level, so which is good in terms of literature reported values. And there was only small things that we had to do regarding this formulation. The K, in fact, K is generally 2600. The Nanonics actually reporting right there. So we said, well, this is saying it's 100 micron, but is it really 100 micron? How do I verify that? Well, maybe we can simulate it in COMSOL realistically and see how it is. So what we did is we simulated the whole nanoindentation in COMSOL by using the material, using the radius of curvature, and obviously we couldn't indent all the way to 200 nanometer because it's huge. The meshing was a huge issue in COMSOL. Well, AUP was able to actually indent up to 10 nanometer, and the values that we got is about 30 micron Newton level, and in the previous one, so 30 micron around here, which is about 10 micron too. So this is, we could simulate only this part, really, because of the computational limitations. So everything is so far so good. Then we went to soft materials, which we really wanted to do because we want to analyze or at least find out how we can accurately measure the Young's modulus of the PDMS. So we couldn't use diamond because diamond would just go through the PDMS. So we wanted to use conical glass probes, just like Kit used, and his was 20 nanometer tip. Ours is 15 nanometer. It's the same tip diameter of the diamond. So we had issues in terms of getting the system stabilized because we were using the same setups that we used for the diamond probe. So we finally stabilized it. We had some measurements, but the values that we got were not as good also, and we figured out that this tip as actually for our PDMS was very sharp. It was almost like dipping in water coming out. So it wasn't really detecting the PDMS. So now we are in the process of hopefully getting new probes from Nanonics and doing almost spherical or conical but larger diameter probes so that we can indent PDMS and repeat the multi-probe measurements for PDMS and hopefully get the actual Young's modulus. Now before I get into the biological components again, now Nanonics tool is designed for enzyme applications and it's great for it. And obviously there is some force reading capabilities. But we need to verify all those force readings for the software, for the materials, for the whether it's changes between diamond probe or a glass probe. Because if you're pressing on a hard material, you may your equipment may have different response with respect to it versus you're pressing on a soft material. So the spring constant was an issue, and we shared with Nanonics, and now we are working on to make sure that this is right for right in the software as well. And one last thing for that is now we are getting a new tip or new setup where the spring constant is higher, about 7,000. So with the higher spring constant, with the tuning forks, we are hoping that when we do nanoindentation on silicon, we will have nicer graphs and nicer force readings. Now, as I said, our goal is to come up with a device where you can actually grow cancer cells and look at their behavior and determine how invasive the cancer cells are. And we have some idea about how we can see those changes chemically. We will put some chemical in this. With the chemical, without the chemical, you know, we have biomedical engineering people in our group, so they are helping us on that. But what we do is simply we created SU8 molds, and then we put PDMS, pressed PDMS on it, and then created these PDMS pillars. On top of the PDMS pillars, we are putting fibronectin, which is the material where the cells actually get food so that they can grow and move around. As they move around, they pull these pillars, and the displacement that they create will tell us the actual forces that they create during their motion. That is the console simulation again for the pillar structure we have, PDMS pillar structure we have, and we sort of know what force levels that we would like to see when the cell is pushing this. But again, this is changing based on what type of, what value of Young's modulus you enter the software. So you cannot depend on the simulation all the time. You cannot depend on the tool all the time. So you have to sort of match them back and forth, and hopefully they both support each other.
Excuse me.
Yes.
You have the cell. Is it covering more, exploring more than one pillar, right? It's like
Yes.
3 pillars.
Yes. Yeah. In fact, in the literature, right now we have 5 micron diameter, 20 micron tall. In the literature, there are 3 micron diameter and 9 micron tall as well. But they made those using deep reactive ion etching, which we have now. We are making them too. But the idea is, if you have the pillars dense enough, you can assume that the cell is actually moving on a flat surface. That's the basic idea. Now, while obviously a lot of people are doing the similar work, they don't want to give up that AFM tips basically do the same thing, right? There are papers that where you use AFM tip with an angle, you come to the pillar and then pull it a little bit, look at it from the camera, measure how much the change is X, and based on the height, you can actually guess the curvature. Using the curvature, you can backtrack the Young's modulus. And obviously, this has issues in terms of pulling forces. You don't know exactly how much force you're applying, because its AFM tool is designed for downward pull, not push, not pulling. And there are other methods where you actually turn the pillar 90 degrees and then push on top, which has also some issues regarding deformations. So that's because of these limitations, we are still pushing to use Nanonics tools so that we can actually achieve what we want to achieve regarding measuring the Young's modulus of PDMS. Now, this was a discussion Aaron would remember from one of the early Skype, because we said, well, we don't have a thin film of PDMS. We have arrays of pillars. And I want to measure the Young's modulus of that specific pillar structure so that I can measure the deflection that they create, the cells create, and then calculate the forces for those pillar sets. So we were talking about by pushing the pillar from one side and then coming with a second probe and measuring the curvature. which would give you the most accurate readings if it is possible, if we can make it. Of course, there are limitations. First, you have to, this force that you are applying has to be known with a good precision. Second, this is a soft material, this is tip, which is touching, and then you are measuring, so that's another issue where it has to detect the zero equal to, z equal to 0 point very precisely, and there shouldn't be any, as Dalia was mentioning today, if you have high frequencies, you may not get good reading. So this is seen to, we are waiting to see whether how this will work. But we would like to do this too. Can we actually take a probe and put on top of the pillar, push it down, very, very small indentation, and then measure with the second and do the same calculations instead of thin film or film structure PDMS. So this is basically in a way, our next step after we complete the silicon nanoindentation and having the forces completely clean. So obviously, ultra-sensitive resolution and keep measured very small, piconewton level forces. And we are hoping to do the same thing with the spherical probes in the PDMS, just thin films first, and then we go to 2D and 3D mechanical characteristics of PDMS. Because in the biological cell research, when you're looking at the dynamic behavior of the cell, you don't want to just look at the 2D behavior, because the cancer cell doesn't move 2D in your system, they move 3D. So maybe not with AU, but later on, we would like to grow the cells inside the pillar as they move in the pillar forest, and we look at the changes that they create in the pillars and measure their forces, how much forces they actually apply in different directions. Well, I mentioned about the high spring constant. Hopefully that's going to be our next. Hopefully next week we will arrive and we'll try that. And go ahead.
The high spring constant is not necessarily for the lateral force, right?
Yeah.
Because that's going to be a soft.
It's going to be, yes, exactly.
Right.
So what we will try it on the silicon first.
Yes, of course.
Yes. And then hopefully we'll do the 90-degree apparatus and be able to push from the side, and then or measure from the side and get the curvature. So now, if we can manage that, that actually opens up a lot of other research opportunities. Sidewall imaging is one of the important things that people are working on, not just for the biological purposes, even the IC guys are very interested in that. And thank you so much for inviting us, and hopefully we'll report good results and we'll see it in conferences, which Ayub is going, when was the conference? August 28th in Michigan, IEEE Nano, he's going to present the Michigan findings. Thank you. So only 3 minutes left for the break.
Other questions?
I made the timer. Kalia.
Have you, I know this is still work in progress, have you thought about trying to add the dynamic element to this? So that you can do dynamic moduli? Because now you've got this quartz tuning fork, right, with very high, very high frequency, high Q. You could have it's a very unique measurement that really only your system would be capable of.
Exactly. We are interested in very high end. There are people that are trying to do the same.
Yeah.
But we want to make sure this is done.
Right. No, this is step one. The quasi-static
Exactly.
is step one, but you are thinking of
Definitely. Because you have a system where it's vibrating nicely, high Q factor.
Exactly.
Why not use it? Yes.
right.
Yes.
And it could be a very powerful tool.
Exactly.
Okay.
Please.
Very interesting talk. How do you compare your technology with, say, microsphere or pillar-based traction force spectroscopy, or basically soft, I would say, mechanical tools rather than using chips?
You mean accuracy-wise, how accurate?
Right, exactly. You know, how would that compare with accuracy or?
Well, in the literature, the calculating traction forces from pillars, people have tried, and they have some good success. The other methods also require actual pulling the cell.
Right.
That requires a lot more. We don't have that capability, first of all. So we don't have a way of comparing. But AU probably has any answer to that, whether pulling the cell versus just letting cell pull the PDMS pillars.
There are some simulations as well as different type of measures, but in terms of the computational efficiency, most alternative best because they're decoupled in terms of patterns.
Because
our intention is that the very high resolution of force with this tool, we're able to mimic the actual cell force of nanometer scales, which shows what the